Okay, so here we have some slightly more complicated circuits. First, we want to establish that we start with 6 volts, so that's our total voltage, and then take care of any resistors that are in series that we can go ahead and just add up. For instance, this 4 ohms and 2 ohms are in series with each other, so we can say, okay, that has an equivalent resistance of 6 ohms. At this point, we can redraw our circuit, and this is a very simple redraw. And we'll draw this line as well. And we have our 3 ohm resistor here and our equivalent resistance of 6 ohms here. And then we have our 10 ohm resistor, which is just hanging out up here. Okay, now if you notice, the 3 ohm resistor and the 6 ohm resistor are in parallel with each other. So we can use the formula for total resistance, which is going to be, I like to rewrite it as 1 over the first resistance, which the equivalent resistance for that line is 3, plus 1 over 6, because that's the total resistance for that line. And we get 1 divided by 1 over 3 plus 1 over 6, right, 2 ohms. So we can actually redraw this again to make an even simpler circuit. Where we have 2 ohms here. Alright, so now we can find our total resistance. See, I did resistance in purple. Now that this 10 ohm resistor is in series with an equivalent resistance of 2, we can say that our total resistance is 12 ohms. We also know that our total voltage was 6 volts. And we can use V equals IR to find our total current. So V was 6 and R was 12, which makes our current 0.5 amps. Total current, 0.5 amps. Okay, so we know that this equivalent resistance and this resistor of 10 ohms has a current of 0.5 amps. We can go ahead and find the voltage used by each resistor, because it'll be equal to V equals IR. Well, since I is 0.5 and R is 2, this guy uses 1 volt. And then current, which is 0.5 times 10, our 10 ohm resistor uses 5 volts. So we're going to back this up. We know that this is 6 volts. We know the 10 ohm resistor uses 5 volts. And then now that we've split this up, it says, okay, the equivalent resistance of 2 ohms gets 1 volt. Well, guess what? When you're in parallel, if one line gets a certain voltage, the other line gets a certain voltage. Because if you back up, it's not going to change until we hit something, which, when we go backwards, the first thing we hit is our battery, which gave us all of our voltage. Anyway, we can find our total current by saying voltage divided by resistance. So 1 volt divided by 6. So our current down this line is 0.167 amps. And then the current down the other line would be 1 divided by 3, which is going to be 0.333. Repeating. Alright, notice that those two numbers together give us our total current of 0.5 amps. Okay, once they join up here. Here and here. Alright, So we can back up to our original circuit. We know the 10 ohms uses 5 volts. We know this 3 ohms, since it's the only one out there, uses 1 volt. But now we need to split these up. We know the current is 0.167 amps, so we can find the voltage that each one uses by taking the current and multiplying by the resistance. So we'll start with the 2 ohm, and it uses 0.334 volts. Oh, that's dark of the one. 334 volts. And then the other one uses, see, we take our current, multiply by resistance, and it uses 0.668. Okay, and then we go through the 10 ohm resistor, and by the end we have 0 volts. And we're going to have 0 volts until we go through this 6 volt battery, and then the long end is the positive end of the battery, and that's always the direction that the current is coming out from. So this is moving clockwise. Okay, so we know the voltage that each resistor is using. We know the current for each line. We could go ahead and figure out the power, which is going to be the voltage times the current. So the voltage used by the 10 ohm resistor times its current will give us 2.5 watts. Looking at the 2 ohm resistor, the voltage it used was 0.334 times its current, 0.167. It used 0.056 watts. The 4 ohm resistor used 0.668 times 0.167, so 0.112 watts. And then the 3 ohm resistor had a voltage of 1 times a current of 0.33, so it used 0.33 watts. So since wattage or power is a brightness thing, the one with the greatest power will have the brightest light. So if these are all light bulbs, the 10 ohm resistor would have the brightest light. Alright, we should be able to map our way around the circuit and get back down to 0. So considering that we started with 6 volts here, and then let's take this path. We went through the 2 ohm resistor and lost 0.334 volts, then we lost another 0.668, and then another 5, and we should end up with 0. And if we do, we have a pretty good hunch that we did this right. So 6 minus 0.334 minus 0.668 minus 5. And it should be close. It might be off a little because of rounding. Okay, notice we get negative 0.002, which is essentially 0 volts, which is what we expected. Okay, moving on to the second circuit, we have a total voltage of 12, and it's going to be 12 volts until it's used up by these resistors. So we want to go ahead and figure out if we can find any equivalent resistances. So notice this 20 ohm and 30 ohm resistor, or these resistors, are in series with each other. So we can get a total resistance of 50 ohms. And we can redraw this . And this is still 100 ohms. This is now an equivalent resistance of 50. And this is still 10. And then we've got our battery, which is 12 volts. Okay, notice that the 100 ohms and the 50 ohms are in parallel with each other. So we can go ahead and use the 1 over 100 plus 1 over 50. Close our parentheses. We have a total resistance of 33.33. So we can redraw this again. So this is essentially 33.3 ohms, and this is 10 ohms of resistance. So now that they're in series with each other, we can find our total resistance by adding them together. So 33.333 plus 10 will give us the total resistance of 43.3333. We know our total voltage is 12 volts. If we have our total voltage and our total resistance, we can find ourselves our total current. So 12 divided by 43.33333. Okay, we get a current of 0.2769. Amps. Or in other words, coulombs per second. Okay, so looking here, we can find out the voltage used by each equivalent resistance. Our voltage is going to be equal to the current times the resistance. So for the 33.333 ohms, it will be the current, which was 0.2769, times the resistance, so 9.23. So it gets 9.23 volts, and the 10 ohms will get current times resistance, which is 2.769. Alright, now we can go back and say, alright, we know that this guy uses 2.769, and we know that if the equivalent resistance gets 9.27 volts, that means that each line gets 9.23. Sorry, each line gets 9.23 volts. And we can use our voltage and our resistance to go back and calculate each particular current, and it should add up to our total current. Anyway, so 9.23 divided by 100 gives us the current for the 100 ohm resistor, which is 0.0923 amps. And then 9.23 divided by our total resistance for that line, because remember we have two in series, we get 0.1846 amps. Okay, this one happens to be going this way, this one is going that way. They join right here, and they should give us our total of 0.2769, which it does. Great. Alright, so here we can go a step further and figure out the voltage spent by each resistor. Now, if we back up, we know the 10 ohms uses 2.769 volts. We know the 100 ohms uses 9.23, because that's how much each line got, and this is the only resistor there. Now, since we know these two resistors have a current of 0.1846, the voltage it uses will be the current times each resistor. So 0.1846, or actually 0.1846 times the resistance, so the first one is 20. That equals 3.692 volts. And then the second one would be 0.1846 times 30. So the current times that particular resistor, 5.538. And those two together should give us a total of 9. So we'll go ahead and double check that. 9.23, yeah. Alright, and we should know that we got to the end of the circuit the right way. So say we chose to go this way. Each resistor that we go through is going to use voltage, and by the end we should get 0 volts. So we started with 12 volts. We subtracted, we went through the 20 ohm resistor and used 3.692. And then we went through the 30 ohm resistor and used 5.538. And then we went through that last resistor and used 2.769. And we end up with 0.001. The reason it's not exactly 0 is because of a rounding issue. But rounding to 3 or 4 decimal places gets us pretty close. And then notice if we go this other way, so through the 100 ohm resistor and then around through the 10 ohm, we had 12. We used 9.23 going through the 100 ohm resistor and then another 2.769 going through the 10 ohm. Notice we get 0.001 again. So we know we got that pretty close. Alright, we can find the power that was generated by taking our voltage and multiplying by the current. So the voltage for the 100 ohm resistor was 9.23 times its current, which was 0.0923, and we get 0.852 watts. The 20 ohm resistor spent or used 3.692 volts and had a current of 0.1846, so 0.682 watts. The 30 ohms will be the same current, 0.1846 times the voltage it used, 5.538, 1.022 watts. And then last but not least, the voltage used by the 10 ohm resistor was 2.769 times its current, which was 0.767 watts. Okay, we can take our total voltage, which is 12, and multiply it by our total current, which was 0.2769, and we get a total power of 3.3228. Okay, we should be able to add up all of our powers. And get that same total. Or roughly the same total. And we get 3.23, which is really, really close. Alright, so we know that we have a pretty good feeling that we did this correctly.